171 class. This is the fourth and final part of the notes for section 3.5. And here we're doing modeling data. And this is something that you're going to do in your functions project for the end of the semester. And what it basically does is it's talking about you collect data. You've got bivariate data, meaning you have each point represents two things. Like this could be, hypothetically, X could be shoe sizes, Y could be height. And as shoe sizes are getting bigger, the heights are getting bigger. Okay. If it's going downhill like this, that could be something like hours spent playing video games and your grade on your pre-calculus test. Okay. So the more you play video games, the lower and lower and lower your grades are. Okay. Again, these are hypotheticals, but what data does is it gives us trends. When we plot the trends, these things are called scatter plots. And a scatter plot is just the dots that we use to collect that bivariate data. But what we do once we plot it, once we see the scatter plot, we can see a trend in the data. And here this looks like a line kind of goes through that data. All right, a line goes through this data. All right, but this over here, a line doesn't do that well for either of these. It's definitely not linear for these last several types. But the first two definitely linear models. With the other two, we use an exponential model when we see that upward bend like that, or if we're going down but we're kind of bending upward as we go, we're kind of like an airplane landing. We have that horizontal asymptote. That's exponential. And then if we are growing but we're bending downward as we grow, right? This is growing but bending upward. This is shrinking but bending upward. This is shrinking but bending upward too. So there's a little crossover you could have with logarithm and exponential when you're talking about that. If b is your model is negative, has a negative number in front of the natural log, whereas here that would still be a positive base, positive numbers. It's just fractional, so we're decreasing. So there is a little bit of crossover with exponential logarithm, but when b is positive, b is greater than 1, when we're talking about these two different models, there's a definite distinction between the two. So this is growing but bending downward, this is growing but bending upward. So what are the things that you're going to have to be able to do on your functions project is collect data, look at the data, and know what to use to model that data. So I'm going to show you how to use Excel to help you with this data stuff. Alright, a lot of the homework in this section, you just have to make the scatter plot and determine what looks the best. But I'm going to show you how to do Excel because that's ultimately what you're going to do on your functions project. Alright, so the first thing this wants me to do is create a scatter plot for the data. So what I'm going to do is I'm going to open up Excel and I'm going to type in exactly what these two things are at the top. So age of death, savings needed. Alright, first thing to notice, in the default, the size of Excel's windows or the cells, they are, a lot of times, they're not that big and they're not meant to have a whole lot typed in it. Typically they're numbers. But if you go, like the age of death went beyond the border here, you just go up here and notice this cursor that's got the white cross now. When I go up into the names of the cells, in between A and B, it turns into that double arrow with a black line in the middle. If I double click that, it expands enough to cover the whole entire name of the cell. So same thing, I can double click that and get it to be big enough for the category names. Okay, and then I just fill in the numbers. Now, notice I've got the ages as they are, as they're written, but the savings, anytime that you can make the numbers smaller in Excel, especially if there's a large disparity between them, it makes the model much easier to work with if you can make the numbers that are much bigger smaller. And the way we can do that here is to say that this second column here is measured in thousands. So I got 219, 307, 409, 524, 656, but that's the savings needed in thousands. So because all these are thousands. So once you get that down, your model will be a lot nicer to work with. So what I'm going to do is let me blow this up so you can see it a little better. I'm going to highlight the data. I'm going to click on age of death and hold my click and go all the way down to make sure I have all the data points, and then let go. And then I'm going to click on insert and then the scatter plot. So that's the first thing we're asked to do, is find the scatter plot. So this is what Excel returns, but it's giving me all this negative space that's not being used here. So this is what I always do. I always delete this. I don't need that. But because our smallest data point is 80, and this is going from 0 all the way up to the 80, I'm going to double click on any of these horizontal values. And then up here where it says minimum, right now it's at 0 on auto. I'm going to switch it to fixed, and it says 80. I'm just going to do 75. I always go a little bit below. And then I really don't need to do it here. I mean, I can see the scatter plot well now, but same thing. This goes to the smallest data value is 200. So I'm going to click the 0 here and change this to, I'll just change it to like 150. Alright, so there's my data. I can see it well now. It gives it a title based on whatever's in the second column, and it always, when it makes these graphs, when you do the insert scatter plot, it's assuming this is your X and this is your Y if you write it that way. So just know to put in whatever you interpret to be the independent variable here and the dependent here. Okay, so the savings needed depends on the age of death. So dependent variable, independent variable. Alright, so now I'm going to model the data. So put a model in here. So the way we do that is just right click any of these data points, right? Any of these little diamonds in here, the data point. If you right click that, it'll give you the option to add a trend line. So right here is add trend line. I'm going to click that. Then I'm going to move this over so you can see. But linear right now is the default trend line that you get. That's why it's called a default trend line. They're going to default to linear. But you can switch it to exponential. Alright, you can switch it to logarithmic. For your functions project, you'll also use polynomial, and you change the order and the degree higher and higher and higher. Alright, well, higher up to 6. That's as high as it'll go. Alright, but what I want you to be able to do is right here where it says display equation on chart. That's actually your model, and that's what the third part of this question is asking. So we click that, and then also display R squared value on chart. Click that. Now R squared is what's going to determine what model is the best. So right now, this 0.9939, think of that as R squared is like a grade, right? R squared is like a percent error, how the model misses going through directly the center of these 5 points. Right, so it's doing pretty good, 99.4% accurate roughly. But if I switch to exponential, I get a different model, and notice the R squared changed. 0.9932, it's not quite as good as 0.9939. So the linear is a little better because basically, I mean, this is basically a straight line. And then logarithmic, again, it shows you a picture of what your data would look like to use these models. Logarithmic, it really, again, it doesn't bend that way. So 0.9877, it's not as good a fit as the linear was. All right, the linear was our best fit. So we can go back to the actual question asked. The linear function is the best choice for modeling the data. We've already got the scatter plot. Excel made our scatter plot for us. All right, and now we just need to come up with the model. Well, Excel also does that for you too. Right there above the R squared is your model. So I'm going to copy that, paste that in here, and there's a model. Now, Y, again, was the savings needed, so I can maybe put an S there for savings. And X, the independent variable, is the age of death, so I'll put A for age. And there's a model. How much savings do you need? You take your age, multiply it by 21.82, subtract the 1540, and that's the savings needed in thousands. So you would need to multiply by 1,000. So for instance, 21.82 if I died at 80, so times 80 minus 1540.8, I need that times 1,000. I need 204,800. Alright, this says 219,000 actually, so pretty close. And then if I did, let's do the 90, one right here in the middle. Alright, do 90, I need 423 times 1,000. 423,000, so 409,000. So again, it's a pretty good approximation. The model has given us a pretty good approximation of these numbers. Again, it's just because of the way we entered the data, it's in thousands. So 532, 524. So that's what a model is designed to do. Is take data, give you something that goes through the data pretty well, pretty accurately, and can estimate other values. Now we don't, again, we knew these values, but I could say, well, what if I died at 75 instead of 95? What would that be? So that times 1,000, so 95,700 roughly. So that's what the model is used for. That's how we use what the Excel has returned in this spreadsheet. Okay, easy just to copy, put the numbers in there, drag over it, insert the scatter plot, everything that you need to do with Excel. It's not that bad once you've got your data. Alright, intensity and loudness. This is the intensity in watts per meter of a sound. This is the loudness of the sound measured in decibels. So we can put this in, so insert scatter. Alright, I'm going to delete that. Again, I got a lot of negative space right here. Right, the lowest number I have is 110. So I'm going to double click. This is fine. Okay, I have a number that's really close to 0. I have a number that's at 100. So horizontal is fine, but vertical, I don't need anything in the zeros and 20s. So I'm going to double click this, change that minimum again to 100. Alright, now I'm looking at that. I'm going to right click, insert trend line. Linear, I'm going to click on display equation, display R squared. Linear, I see when I plug that in, linear, it's missing this point, it's missing this point. R squared is only about 0.67, that's like a D, as far as a grade goes. That's not a very good model. Alright, exponential, 0.64, that's even worse than linear. Okay, and the problem is this bends downward, and again the picture shows exponential is bending upward. Alright, but if you look at logarithmic, it bends downward. If I click logarithmic, it's perfect. Right, it's going through the points exactly. When R squared is 1, that means 100. That's like you made a 100 on the test. It goes through, it slices through every single point on this thing. It hits them perfectly. So this is a perfect model, this logarithmic model, and it's because the relationship between intensity and loudness is logarithmic. But it's a perfect model here, and that is the model that we would use. So I'm going to grab that model and do the same thing we just did. That's the model for this thing. And if I type in 4.3429 times the 29 times the natural log, first number, 0.1, and then I add 120, I get 110 point virtually 000, virtually just 110. And then if I type in 10, I'll skip down to the 10 one instead of the 0.1. I get 129.999, basically 130. So this model hits everything almost perfectly. And it's a very, very accurate model. Right? Log would definitely be the answer to which one works the best. But that's your model. You get your model directly from Excel. Now, a lot of times they'll tell you to use like Y as your variable, so that's loudness in decibels. So I would put D for decibels. And then X is my variable. in its intensity, so maybe I would put high for that. Okay, so anyway, a model is just how to get one variable from the other. That's what you're doing a lot of on your functions project.